In on today, study assignment F, which should be about sort of the redox reactions and stuff that we've been talking about. So study assignment F, which is about redox reactions, obviously. Now, up to this point, we've talked a little bit about, I guess a lot about it, I suppose, in this last chapter, about redox reactions, also about the idea of oxidation number and what is being oxidized, what is being reduced, what is the oxidizing agent and the reducing agent. And, we talked about sort of balancing redox reactions and maybe sort of simple terms in terms of half reactions. So for example, if we had, let's do maybe like magnesium plus some oxygen going to magnesium oxide. And need a 2 there, I think, and a 2 there. And again, what's happening in this situation is the magnesium is 0, oxygen is 0. Magnesium here is +2, oxygen is -2. In this particular case, again, if it's helpful for you to use that sort of number line approach, we do see our magnesium going from 0 to +2, which means it's going through oxidation. And again, our oxygen, as we saw, going from 0 to -2 in this case, going through reduction. That again means that our magnesium here going through oxidation would be our reducing agent. And the oxygen here that is going through reduction would be our oxidizing agent. Now, if we took this equation and we broke it off into its half reactions, basically remember that a half reaction, basically one of them represents the oxidation half reaction and one of them represents the reduction half reaction. So in this case, it would be the magnesium here going to really our 2 magnesiums with a +2. And again, to sort of break it off into its half reactions, really, you're just going to really pick the 2 things that are really related to each other, the same things on opposite sides of the arrow. O2 would be over here, going to O2 minus here. Yeah, so in this reaction, it would take place. You probably could have safely assumed that this reaction would take place in this sort of synthesis reaction. Really, for the most part, it's really those kind of single replacement reactions that you really want to would probably be a reaction where you might not see a reaction occur based on reactivity. So that was the one where we kind of saw that activity table. And it'd be more of a single replacement reaction. This reaction definitely would take place based on just, if you remember those sort of 3 premises for why reactions occur. One is an electron transfer, one is making a precipitate, and one is making water. So really in this case, for sure, we know just based on, what we talked about with bonding, electronegativity and stuff like that, we really have a metal here and a non-metal. And again, whenever a metal and a non-metal get together, it's a pretty good sign that we're going to get that transfer of electrons that are going to occur. So this is almost for sure going to happen. You don't really have to worry too much about whether or not, this reaction would necessarily take place. It would be more so in that situation, more of those single replacement reactions that we talked about towards the end there, that, is potential you could maybe not have a reaction take place. Not necessarily a redox reaction, but the other place where, you might not have a reaction occur is where we saw with our double displacement reactions where, we basically made everything that's aqueous, right? We didn't really have any precipitate form. We didn't have water form. All the ions canceled out. So in relationship to double displacement, that would be a situation where perhaps a reaction would not occur. And in case of sort of a redox reaction, it would be more in this sort of classification, those single replacement reactions. Again, probably safe bet for a synthesis or a decomposition or a combustion reaction would probably take place in most cases. Other questions on that? Okay. So once we have it split off into our two half reactions, remember one's our oxidation half reaction here, and one's our reduction half reaction. We want to put the electrons on the proper place, and in this case, it would be 4 electrons on the product side. Remember that this indicates that this is an oxidation half reaction when you do see those electrons on the product side. The reactant side here of our second half reaction is where we would add those 4 electrons. And because the electrons are on our reactant side, again, as we talked about, that's like them being added, and that's considered a reduction half reaction whenever you see electrons on the reactant side. Now, when we have these half reactions and we want to add them back together, it's always important that the electrons are balanced. And in this particular case, because really I started with a balanced equation and everything, I ended up with balanced electrons on both sides. So we do have, obviously in this case, our oxidation half reaction and our reduction half reaction. And let's just take a second here and talk about each of these half reactions. They're balanced, and it's really important to make sure things are balanced as you kind of go through balancing these redox reactions, obviously. And when we talk about balance, and especially when we talk about balance in terms of redox reactions and the ones we're going to talk about here in just a second, we're talking about being balanced in really 2 ways. And it's really important to keep that in mind. One way is like a normal sort of equation. We have the same number of elements on each side of the arrow. So for example, here, if we look in our first half reaction, we have 2 magnesiums on the left, 2 magnesiums on the right. We have 2 oxygens on the left in the bottom one. We have 2 oxygens on the right in the bottom one. So kind of like a normal balancing of an equation, you want to always make sure that you have the same number of elements on each side. The other also really important thing, especially with redox reactions, is that you have the same charge or total charge on each side. So what do I mean by that? Well, what I mean by that is if I look on kind of the left-hand side here of the magnesium half reaction, the overall charge is 0, right? Magnesium has no charge in this situation. When I look at the overall charge on the right-hand side of this reaction, 2 times plus 2 is plus 4. 4 times minus 1 for the electrons is minus 4. When I add those guys together, I end up with 0 as well in terms of the charge. So the charge on the left-hand side of my half reaction for magnesium is 0. Charge on the right-hand side of my half reaction is 0 as well. And that's always something that you want to make sure that you achieve. We can see the same thing if we look at the bottom here. Overall charge on the left-hand side, 4 times minus 1 is minus 4. And this is 0, the oxygen. Oxygen on the right is 2 times minus 2, which is minus 4. And this is also another important point to remember when we're balancing redox reactions is the charge needs to be the same on both sides. It does not have to be 0 on both sides. So this is technically balanced because on the left-hand side of the arrow, we have a minus 4 overall charge. On the right-hand side of the arrow, we also have a minus 4 overall charge. Any questions on that? Now, technically, once we have the equations balanced in that sense, the other really important thing that we do have to kind of keep an eye on is the electrons. And we need to watch out for kind of two things. One thing comes a little bit earlier on is whenever we put electrons into our half reactions, which we'll do here in just a second, actually put the electrons in ourselves, we always want to make sure that they are on opposite sides of the arrow. You should never ever add electrons to the same side of the arrow. And the reason for that is, as we talked about, when there is an oxidation, there is always a reduction. So when we have an oxidation, there is also always a reduction that occurs. And really the process here boils back down to this. It's all about the electrons being transferred. We're essentially transferring electrons from whatever is being oxidized to whatever is being reduced. So however many electrons are kind of lost by the oxidation guy is how many electrons should be gained by the guy going through reduction. Any questions on that? So with that being said, sometimes when you get to these half reactions, for example, maybe you wrote it in such a way where you really didn't balance it to begin with, and you ended up maybe with something like this. And maybe for some odd reason you did balance the bottom guy and you had the bottom guy balance. I'm not sure why you would do the bottom without the top, but we'll just use it for this example here. And before you could add these back together, you do need to make sure that you have the same number of electrons in each half reaction. And the idea behind that is because the electrons are being transferred from the guy being oxidized to the guy being reduced, when you add these half reactions back together, the electrons should cancel out 100% completely. They should not be there anymore. If I were to add these back together just like this, I would basically be taking 4 electrons minus 2 electrons, and I would still have 2 electrons, which is not good. So sometimes when you're in this situation, you do need to take a half reaction, and it may be one of the half reactions. It may actually be both half reactions sometimes. And you sometimes need to multiply the half reaction by a number to get the electrons to the proper number. So if I did that, that would be multiplying the entire top guy by 2. And now what I will have is my balanced top equation with 4 electrons to go with my 4 electrons in my balanced bottom equation there. And now because I have the same number of electrons on opposite sides of the arrow, they really do cancel out. So I'll leave them not canceled for a second and then we'll cancel them out. But basically what we do is we add these together by keeping everything on the left-hand side of the arrow on the left-hand side of the arrow, and everything on the right-hand side of the arrow on the right-hand side of the arrow. And you can treat the arrow almost like an equal sign in math, which means I could kind of subtract the 4 electrons from one side to the other, and they will essentially cancel each other out. And what we will be left with is the overall reaction at this point of 2 magnesiums plus oxygen. And when these 2 magnesium ions get near these 2 oxygen ions, they're going to come together and form our magnesium oxide. Any questions on that there? So in a simple sort of straightforward redox reaction where you have your oxidation reaction and your reduction half reaction, you want to always make sure that the electrons are the same number in each half reaction before you would add those back together. And again, like I said, you may need to multiply by a common number to one of the half reactions, or actually sometimes, like I said, both of the half reactions. So this is sort of a more simple redox reaction. Any questions on that? Now that we have sort of this foundation, let's talk a little bit about a little bit more complicated redox reactions like the ones that you will see in that study assignment, and also that you'll need to know how to do obviously for this class as well. And these involve redox reactions where we balance things in either acidic conditions or basic conditions. So a lot of times when we're doing sort of redox reactions, a lot of times it involves electrochemistry like galvanic cells and stuff like that. A lot of times there's solutions involved. And a lot of times we either do these things in basic or acidic conditions. So when we are balancing equations in basic or acidic conditions, there's a few more steps along the way that we have to take to balance these equations. There's a few different approaches that you could take depending on whether it's acidic or basic. The easier approach, in my opinion, is to just start with, I'm going to assume everything is going to be in the acidic conditions first. So the steps that we follow when we're balancing a redox reaction in acidic conditions is the first thing you want to do is you most likely will have the unbalanced equation given to you. And most of the time in normal situations, not the study assignment, we'll talk about what's in the study assignment at the end here. But in normal situations, they'll give you the unbalanced equation and they'll put next to it like acidic, or they'll put next to it basic, which implies that you need to balance this equation in acidic conditions or basic conditions. Now, if it's acidic conditions, after you take the unbalanced equation, you then want to break it up into the half reactions. And what are the half reactions? They are the oxidation half reaction and the reduction half reaction. Now, it probably will also be good, maybe back here as well, to figure out what is being oxidized and what is being reduced. You know, take a moment to kind of figure that out before you kind of jump into the balancing part, because it will help you when you get down to here to make sure that you actually are writing the equations correctly. Now, once you have broken it up into a half reaction and an oxidation half reaction and a reduction half reaction, you're then going to balance all the elements except for oxygen and hydrogen. So how are you going to go about balancing these? You're going to balance them the exact same way that you would balance a normal equation. You would add a coefficient. So, you know, if you had like 2 oxygens on one side and 1 oxygen on the other, oxygen is a bad example. When we try a different one, you had 1 magnesium on one side and 2 magnesiums on the other side. That's a better example, I suppose. You would put a 2 in front of the magnesium on the side that needs it. Now, once you balance all the other elements in both half reactions, then it becomes time to balance the oxygens in each half reaction. And the process by which we go to balance oxygens in half reactions in this type of situation is we add water to the side that needs the oxygen. Now, let's just say, for example, and I'll just, you know, make something up here. We got MO2 on this side and like just M on this side. All right. Forget about everything else. We'll just focus on this. When we look at this, we would see that we have 2 oxygens on the left-hand side. In order to balance the oxygens, we would add 2 waters to the right-hand side. That 2 waters is going to provide 2 oxygens to the right-hand side. And now we have 2 oxygens there and 2 oxygens there. You may also notice that if we add water, we're not just adding oxygen to that side, but we're also adding hydrogen. So for every water that you add to one side of the half reaction, you need to add two H pluses to the other side. And the purpose of the H pluses is to balance out the hydrogen that we added. So in this example, we added 2 waters, which means to the other side, I would need to add 4 H pluses. Again, if you don't do that, you're going to be short hydrogens when it's all said and done, and your equation will not be properly balanced. So because I technically have 4 hydrogens there, I need to also add the 4 hydrogens over here in the form of H plus to make sure everything is balanced. Any questions on that? Also, occasionally, just right off the bat, you may have a half reaction where, let's just say on one side you had like HNO3, and on the other side you had like NO2 or something. Right off the bat, right, I could see have more hydrogens on the left-hand side and I have none on the right-hand side. So this would be another situation where right off the bat, you might want to add an H plus to the other side. Again, if you don't do that, you will be short an H plus. So sometimes you could get a half reaction where, you got a hydrogen on one side and no hydrogens on the other. And if you follow the process with the water and the oxygen and the hydrogens, if you don't take care of that extra hydrogen that you started with, you will end up with not the right number of hydrogens. So that's another situation where, in addition to water, you may want to add an extra hydrogen. Any questions on that? Okay. We obviously would do this for both half reactions. So balance everybody just like normal with coefficients, and that's other than oxygen and hydrogen. Then we balance the oxygen, whichever side needs oxygen to balance it with the other side, gets water. And then to the opposite side of where you added water, you would add 2 H pluses for every water that you did there. This again makes sure that you are not short hydrogen when it's all said and done. All right, now that we balance all the elements, now that we have balanced oxygen and hydrogen, the next thing that we want to do is actually balance the charge in each half reaction. And we're going to do this by adding electrons. So for example, let's just say, we'll just steal that one from previously. We had like magnesium, and on this side we had like this, right? Okay. So we went through all the previous steps. Our half reaction is balanced. By the way, there's no oxygen here, so you wouldn't put any oxygens, right? So you don't necessarily have to add oxygen or water or anything like that. If there's none in a half reaction, don't add the water. So at this point, what we want to do is balance out the charge on each side. So that's what we were talking about earlier. We want to make sure that the overall charge on the left-hand side of the arrow equals the overall charge on the right-hand side of the arrow in each half reaction. Remember, just as we talked about just a second ago, they do not have to equal 0 on both sides, but they do have to equal the same charge. Now, this whole thing has an overall charge of 0. 2 times plus 2 is an overall charge of plus 4. Remember that we are adding negative electrons. So in this case, we would need to add 4 electrons to this side, because that plus 4 and now the minus 4 from the electrons that we added equals 0 on the right-hand side to match the 0 on the left-hand side. Best way to do this is exactly the way I just did it. Sometimes people want to go by the individual element and figure out, all right, this has like a +3 oxidation state. It lost 3 electrons. I need to add 3 electrons. But sometimes by balancing it, you got some other numbers involved. So it's best not to go element by element. Just think about the overall charge of everybody. Because when we look at the overall charge on something, it already takes in account everybody's individual oxidation number. So what I mean by that is if you have on one side NO3 minus, for example, sometimes people, when they get to the stage, want to go individually, what is the oxidation state on everybody, and try to figure out, how many electrons, maybe nitrogen or oxygen gained and all that. And you don't need to do that, because what we learned from our oxidation number talk earlier was when we add up all the oxidation numbers, it will equal the charge. So all the math individually has been done for you. We know no matter what numbers we get in the middle there, this whole thing has a -1 charge. So we would think of it as a -1 charge overall, rather than going element by element in this situation. And sometimes less room for error in that case. Now that we have balanced the electrons, or added the electrons to balance out the charge, this is where figuring out earlier on, what is being oxidized, what is being reduced is a good idea, because when you get to this point and you add the electrons to the right-hand side here, you will know that that should be an oxidation reaction, and that should match what you found out earlier. So it's a good way to check yourself to make sure you are adding the electrons to the proper side of each half reaction by figuring out which one's been oxidized and which one's been reduced. Any questions on that there? Now that we have done this again in both half reactions, we will have the electrons added to one side of the arrow, and the other half reaction will have electrons added to the other side of the arrow, right? Because they always should be on opposite sides, never the same side. We want to make sure that we have the same number of electrons on each side. So again, may require you to multiply or not. You may not need to. But as long as we have the same number of electrons on both sides, we are good to go to add the half reactions back together. Again, same number of electrons on each side. At this point, you would cancel the electrons, cancel anything else that may cancel out. So you may have maybe like a water on one side that cancels with 2 waters on the other side. You may either cancel out or reduce down. And if you do all that properly, at that point, that will then give you the balanced equation in acidic conditions. And this balanced equation in acidic conditions will be balanced the 2 ways we talked about on the other slide. They would be balanced in terms of same number of elements on each side and the same overall charge on each side of the arrow. And that's how you know you properly balanced it in acidic conditions. Any questions on those steps there? Now, what do we do for basic conditions? Well, again, like I said, there's a couple of different ways you could approach it, but this way, as may not seem the easiest, is the easiest approach here. So even if it was basic conditions, you basically would follow the exact same procedure we just talked about. Get yourself all the way down to here, number 8, where you have balanced the reaction in acidic conditions. When you do that, you will notice one thing occur. First off, when you have your balanced equation, either the left-hand side or the right-hand side will have H plus there, along with some other things. What does H plus represent? Well, H plus represents acidic conditions. This thing has been balanced in. Now, once you do that, to turn it into a basic sort of reaction, by the way, you probably will have water on the other side as well. To turn it into a basic reaction at this point, you're going to add OH minus to both sides, equal to the number of H pluses you have. So in my theoretical made up example down there, on the left-hand side, I got like water. And again, there'll be other things there for sure. And on the right-hand side, I have 2 waters. So if I were going to turn this into a basic equation, I would add 2 OH minuses to the right-hand side, and I would add 2 OH minuses to the left-hand side. And that's where we talk about both sides being added. To the side where we added the OH minus and there was H plus there originally, those guys will come together and make water, 2 waters. And I'll have my water on the left-hand side I started with and my 2 hydroxides. Very typical at this point is you will then have some waters you can reduce or cancel out. And if I do that, I would end up with 2 OH minus and 1 water in this case. Again, kind of like subtracting the water to the other side. 2 waters minus 1 water leaves you 1 water that's left over. At this point, obviously you would have a lot more stuff in the equation at this point. At this point, it would then be balanced in basic conditions. How do I know it's balanced in basic conditions? Well, bases involve OH minus. So that tells me I am balanced in basic conditions rather than where it was at the end of step 8 with H plus there, which tells me I was balanced in acidic conditions. Also, when you're done at this point, it should still be balanced in basic conditions the same 2 ways. You should still have the same number of elements on each side of the arrow, and you should have the same overall charge on each side of the arrow. Again, does not have to equal 0, that overall charge, but it needs to be the same number. Question on those steps? Okay, so that's a lot of words. Let's actually put it together here, and let's go through one here together from beginning to end so you can see how to kind of put it all together and hopefully do these here. All right, so let's try this one here. We're going to start with this equation here. And we'll do it in acidic conditions. Doing acidic conditions first here. All right, so first off, probably a pretty good idea to get a handle up front as to what is being oxidized and what is being reduced. So if we simply look at the iron on the left-hand side, it has a +2 oxidation state. Iron on the right-hand side has a +3 oxidation state. Again, if you number line that thing, going from +2 to +3 in that direction means that my iron here is going through oxidation. By default, that means my chromium here is going through reduction. To prove that it is going through reduction, we did this one earlier today. That's -2, -14, +6 on this side for the chromium. That is +3. So that was the one we did earlier today. That if we start here, +6, and ending at +3, moving in the left direction are more negative, going through reduction are chromium. So our iron is going through oxidation, meaning this is our reducing agent. Our chromium here going through reduction, which means it's our oxidizing agent. Any questions on that part of it? All right, let's get into the balancing part here. So let's draw a little line. So the first thing you want to do is break it off into the 2 half reactions. Again, the simplest way to do that is just to take the elements that are the same on opposite sides of the arrow. So clearly when we look at it, iron 2 is related to iron 3. And our second half reaction would involve chromium on the left, chromium on the right. So obviously our dichromate here is related to our chromium on this side. Any questions on that? We already kind of know this is our oxidation half reaction. This is our reduction half reaction from obviously figuring it out here. All right, once we have done this, we're now going to get into those steps. So if you remember, after we split it off into the half reaction, the next thing that we want to do is balance all the elements except for oxygen and hydrogen. Up on the top half reaction, there is one iron on the left, one on the right. We're not looking at charge. We're looking at how many actual iron guys there are, right? So there's one iron on the left, one on the right. On the second half reaction, there's two chromiums on the left and one on the right, which means to balance it just like a normal reaction, we would lay up a coefficient in front of the Cr2 there to balance it. Any questions on that? Okay, next, now that we have balanced all of the elements except for oxygen and hydrogen, it is time to balance our oxygen. Looking at the top half reaction, there's not an oxygen to be found, which means we don't need to add water to either side. Again, you're adding the water to balance the oxygen. When we look at the second half reaction, we see that we have 7 oxygens on the left and none over here on the right. That means that we need to add over here on the right-hand side 7 waters. And we're going to add that 7 waters. What that's going to do is give us 7 oxygens on the right-hand side now, and also 7 oxygens on the left-hand side. As we talked about, though, when we add water to one side of the half reaction, we're not just adding water, but we're also adding those hydrogens, which means if we do not take care of it, we're going to be off in terms of our hydrogens. So in terms of hydrogen, we have added 14 hydrogens to the right. So to make sure we're not unbalanced, we would need to add 14 H pluses to the left-hand side. And again, that is to balance our hydrogens that we added from the water. Question on that? Okay, so far we're following through those steps. We balanced all the elements other than oxygen and hydrogen. We have now balanced the oxygen by adding 7 waters to the right-hand side of the equation that needed the oxygen and 14 hydrogens to the left-hand side that needed it. So what do we do now? We're up to the point where we want to balance the charge in each of these half reactions. So we're at the point now where we want to add electrons to balance out the charge. So what I'm going to do is just kind of rewrite it here so we can kind of see what's going on. All right, give me a little bit more room because I think I squeezed too tight in there. So rewriting the top guy looks like this. Rewriting the bottom guy now, we have 14H pluses plus Cr2O7 2 minus 2 Cr3 plus and 7 waters. All right. Now, when we go to balance this, overall charge is really the best approach. So overall charge on the top here is +2. I'll write it on this one so I don't mess up on the bottom one there. Overall charge on the right-hand side is +3. Remember, we need to get them equal to each other. And the only way we could do that is to add negatively charged electrons. And what that means in this case is we need to add 1 electron to the right-hand side. Again, by adding that 1 electron to the right-hand side, that gives me a +3 and a -1, which is a +2. That balances the +2 that we have on the left-hand side. So this equation is balanced in terms of charge. Any questions on that? Now, earlier we determined that this was our oxidation half reaction. Can we make sure we did kind of the right thing? We can, because we see that we are adding the electrons on the right hand side, and that is definitely what you do in a oxidation half reaction. So again, that's a good way to check yourself when you're doing this, to make sure you're adding things to the proper side. We now want to do it to our bottom one here as well. Now, as I mentioned earlier, it's best just to use the overall charge here to help you do that. So what I mean by that is, if we look at this 14H pluses, that's basically a plus 14 charge. Now this dichromate has a lot of things going on there, but who cares about their individual oxidation numbers? Because the overall charge is -2, which is pretty much the sum of all the oxidation numbers. So might as well just look at it as -2. Since the work was done for you, you don't need to go individually and go, this guy's +6, this guy is -2, and blah, blah, blah. You don't need to do that. It's already done for you right here. Don't redo the work here. Altogether, if we sort of add up both of these guys, +14 and -2, gives us a grand total of +12 for the left-hand side of this second half reaction. Let's look on the right-hand side. We have 2 chromiums that are +3. 2 times 3 is +6. Water is 0, right? It's neutral. So we have over here +6 and 0 is +6. All right, so we need to get these guys to the same exact charge on each side. Again, we're adding negative guys here. So in order to do that, we would need to actually add electrons to the left-hand side here. We would actually need 6 electrons, which is why I rewrote it. So I'll put it down here, 6 electrons. And when I do that, I now have +12 plus -6 gives me a +6 on the left to match the +6 that I have on the right-hand side. So that will balance the overall equation for our second one. We also know that this is a reduction half reaction, and we see we added the electrons to the left-hand side, which is proper for a reduction half reaction. Any questions up to that point?
Can you go over how you got the 6 electrons?
Yeah, to add to the second one.
Yeah.
So let me just mark here. So I scribbled. So we had basically just looking at that half reaction by itself. We had 14 H pluses, and we had our dichromate at this point. And on the other side, we had this and 7 waters. So this is what we had before. Obviously, we added the electrons in that half reaction. So again, really the best way is just to go overall charge on each side. What is the overall charge you have happening on the left-hand side? Well, these 14 H pluses, because hydrogen's +1, is going to contribute +14 in terms of overall charge. This dichromate altogether, since there's only one of it, will contribute a overall charge of -2, which means when we add these together, technically speaking, on the left-hand side of that equation, we have a +12 happening for like the overall charges on the left-hand side of the arrow. We could do the same sort of addition over here. We have 2 of these chromiums, each is +3. That gives us a +6 charge from the chromiums. Water is neutral, which means 0, right? Overall charge. If we add these together on the right-hand side of the arrow, we have an overall charge of +6. Now remember, the only way that we could balance the charge on each side is to add negatively charged electrons. So really we need to add the negative to whichever side will need the negative charge. So when we added our 6 electrons to the left-hand side, and we knew we should add the electrons to the left-hand side because it was a reduction half reaction, those 6 electrons that we added are going to now provide a -6 charge. each electron minus 1. There's 6 of them, gets you to -6, which if we add this now to our previous total, we now have -6 plus 12 gives us a new total of +6 on the left-hand side of the arrow, which now matches perfectly the +6 that we have on the right-hand side of the arrow. So we know we should add it to the left-hand side because, again, it's a reduction half reaction. It's gaining these 6 electrons. Question on that? Okay, so coming back here to our 2 half reactions, we again are okay because we did add the electrons to the proper side in each case. Now, what do we want to do at this point? Now at this point, we want to add the half reactions back. But there is a problem in this case because if you remember earlier on, we talked about before you could add these reactions back together, you must always have the exact same number of electrons in each half reaction. And we really don't in this case, right? We have 1 electron in the first half reaction, but we have 6 electrons in the second half reaction. So before we could do that, because we don't have the same number of electrons, we need to multiply, in this case, the top reaction by 6. And again, the reason we're going to multiply the top reaction by 6 is to get us to the proper number of electrons. So what I will do is I'm going to rewrite both of these reactions here. So we want to add the half reactions back. We do need the same number of electrons here. So we're going to distribute that 6 to everybody in that reaction. So if we do that, our top reaction now becomes 6 iron 2s goes to 6 iron 3s plus 6 electrons. Bottom reaction, we don't have to do anything to because we already have 6 electrons. So I'm just going to recopy it. Now that I have 6 electrons in each, and why do we need 6, you think? Well, we know that this guy is gaining 6 electrons. Where are those 6 electrons coming from? They're coming from the 6 iron 2 guys that are each losing 1 electron. So that's where the 6 electrons are coming from. That's where basically this equation tells us that each iron 2 is losing 1 electron. Now that we have 6 of them, that's going to make up the 6 electrons that are totally lost. Now that we do have the electrons equal to each other on opposite sides of the arrow, it's your call. They will cancel, so you could cancel them out now if you want, and that's what I'm going to do. You could bring them down and then cancel them out. It's your call. It's kind of a waste of time to bring them down to cancel them out, but if you want to do it that way, you can. And what we are left with at this point is this equation. Again, everything that is on the left-hand side of the arrow in both reactions will stay on the left-hand side of the arrow. Everybody that's on the right-hand side of the reaction in both arrow equations will stay on the right-hand side. So if I do that, I end up with 14H pluses plus Cr2O7 minus plus 6 iron 2. That should be for both equations, everything that's on the left-hand side of the arrow. Now taking everything on the right-hand side of the arrow, I have 6 of the Fe3 pluses plus 2 of the Cr3 pluses plus 7 waters. If I did this correctly, which I really hope I did, this would be the balanced equation in acidic conditions. By the way, how do I know it's acidic conditions? Well, what do we see over here? H plus tells me it's acidic conditions. Now, let's just make sure really quick that, I didn't screw up, because it can happen. Let's start with the elements to make sure that they're balanced on both sides. So we basically have on the arrow, right? We have hydrogen, chromium, and oxygen, right? So left-hand side of the arrow, 14 hydrogens. Right-hand side of the arrow, 14 hydrogens, 7 times 2. Chromium on the left-hand side, 2. Chromium on the right-hand side, 2. Oxygen on the left-hand side, 7. Oxygen on the right-hand side, 7. I guess iron would be an important one to put there as well. Iron left-hand side, 6. And 6 on the right-hand side. So we have like a traditional equation to balanced it correctly. We have the exact same number of elements on each side. The other important thing, if you remember, is we need to make sure that the overall charge on the left-hand side equals the overall charge on the right-hand side. So let's take a track of that and see what we end up with. Starting here on the left-hand side, there's 14 hydrogens. That gives us a plus 14 on the left. There's our 1-dichromate, just like we did up here. That 1-dichromate is minus 2. There are 6 iron 2s. 6 times plus 2 is plus 12. That means that when we add this all together, plus 14 and plus 12 is plus 26. I should get my calculator. Minus 2 gives us a grand total of plus 24 on the left-hand side of the arrow. Any questions on how I got those numbers? Doing the exact same thing on the right-hand side of the arrow. 6 times plus 3 from the iron on the right-hand side. So 6 times plus 3 is plus 18 coming off of there. We also have 2 times 3 plus for the chromium is plus 6. Water is 0. Adding that together, 18 and 6 is plus 24. We are balanced correctly in this case, both ways. We are balanced by the number of elements on each side and the charge on each side. It equals each other. Again, it doesn't equal 0 as you can see, but it does equal each other. Question on that? Okay, so what we have just done is we have balanced this equation in acidic conditions. Now, we'll use this one to demonstrate what you should do for basic conditions as well. Let's say that this problem wasn't acidic conditions, but it was balance this thing in basic conditions. What would you do? Well, you would do exactly what we just did on this page, all the way down to that bottom equation. And now once you have got it balanced in acidic conditions, you can very easily turn it into basic conditions. So what I'm going to do is find me a fresh page. I'm going to recopy our acidic equation that we just did. So I'm not redoing anything other than just recopying our acidic condition here. So our acidic equation was 14 H pluses plus dichromate plus our iron going to our other iron plus our 2Cr3 plus and our 7 waters. Okay, so again, this is our acidic balance equation. We're now going to turn this into basic. So what do we do to turn it into basic? If you remember, what we do is we actually add hydroxide to each side equal to the number of H pluses that we have. So in this particular case, we're going to add hydroxide to both sides. And this H plus from our balanced acidic condition tells us 14 OH minuses to the left-hand side and 14 OH minuses to the right-hand side. So again, we are going to add it not just to one side, but to both sides, again, equal to the amount of H plus that we have. Any questions on that? Now, as we talked about earlier, the side that has the OH minus and the H plus, those guys are going to combine to make water. How many waters are going to make? 14, right? Got 14 and 14. That is going to give us 14 waters on the left-hand side from the combination of those two guys, and everything else will stay the same. So we're just going to recopy everything else that we got going on here. Now, what typically does happen is you will end up with some water on both sides usually. And in this case, we have 7 waters on the right-hand side. We'll basically subtract off from 14 waters on the left-hand side. It's essentially subtracting the 7 waters to the other side. That's going to then leave us with 7 waters actually on the left-hand side, plus our Cr2O7 minus, plus our 6 iron, going to our 6 iron 3, plus our 2 Cr3 plus, and our 14 OH minuses. At this point, if I didn't screw up anything, always a chance, but we hopefully not. If I didn't screw up anything here, this equation as well should still be balanced both ways. So let's just make sure of that really quick. Again, we have hydrogen, oxygen, chromium, and iron. Left-hand side, we have 14 hydrogens. Right-hand side, 14 hydrogens. Left-hand side, 7 oxygens in the water, 7 more in the dichromate gives me 14. Right-hand side, 14 oxygens in the hydroxide. 2 chromiums on the left, 2 chromiums on the right, 6 irons on the left, 6 irons on the right. We're good so far in terms of elements. We also want to make sure, like we did previously, that the charge is okay on both sides. Overall charge for the water on the left is 0. Overall charge for the dichromate is -2. Overall charge for our iron 2 is 12 plus by multiplying that. Gives us a grand total of +10 if I didn't mess that up. At this point here on the right-hand side for the iron, we have 3 and 6 is +18. For the chromium, we have 2 and +3. I should get the calculator, is +6. And for the hydroxide, we have 14 and -1, which is -14. I'm going to hope that's 10, but let's see here. That is 18 and 6, gives us a +24. +24 and -14 is a grand total of +10 on both sides. This would represent the balanced equation for basic conditions. How do I again know it's basic conditions? What do I have in my equation? No H plus, but I got some OH minus there, which tells me it is basic. Questions on how to go from acidic to basic. Although it may not seem like it, this is the easier way to go from acidic to basic. You actually could add the waters and all that kind of stuff, or the hydroxides early on. It's a lot more canceling out and stuff like that, so it gets a little bit more confusing. Yeah, so was that just the page B? Is this the page you want or the next?
Yeah, I just want to see the page real quick. Yeah, I want to see the final. Oh, you had it just before.
This one?
Yeah, I just copied the few numbers here, and
Yeah, no
thank
worries.
you.
Yep. Other questions on that? So it's important to kind of follow these steps. Obviously, when you're doing it, it's important to, you know, usually based on paper size, we oftentimes have to kind of rewrite a lot of these things. And, you know, the not screwing it up as you rewrite it and stuff like that is really important. It's a very common sort of thing that occurs. Uh, you know, sometimes you will have to you make a mistake just rewriting the thing and stuff like that. All right, now that you've seen me do one, I think you guys should try one yourself here before we really talk about the experiment and the rest of the stuff that you need to do. So let me give you one here. Why don't you copy it down on your paper? Let's go with I minus plus MnO4 minus goes to I2 plus MnO2. And why not? Let's do basic just for, you could do the entire thing. All right. So take a second, copy that down. And what I'm going to do is we don't use breakout rooms too much here. So I'll open up some breakout rooms and let you guys work on it for 10, 15 minutes, 10 minutes or so. We'll come back, we'll do it together just to make sure everybody's at least on the right page here, so that you can do that. So take a second here again and copy it down so you have it. So I think your question is, and I hope this answers much. Let me know. But what's really happening here is not necessarily we're making different elements or anything like that, but really this is again under that classification of a redox reaction. And again, one of those driving forces, as we talked about a number of times, for why reactions really take place is those kind of transfer of electrons and electron transfer. And that electron transfer is really what a redox reaction is. So the process of these guys getting near each other or sort of reacting with each other is there's a certain willingness, if you will, when these guys get together, like the I minus, for example, here, and the MnO4 minus, or in the previous example, the iron and the dichromate. When those guys get together, there's other factors which you'll learn in like 200B, that there's like a willingness that we want that sort of electron transfer to occur. The conditions are kind of really correct for it to happen, and it will sort of happen spontaneously. It will just kind of naturally occur. And the basis of why it occurs is really because of that transfer of electrons that is going to occur. And it's kind of going to drive this reaction to sort of take place. Break this off into the half reaction. So really the simplest way is just to find the two things that are pretty much the same element. So we would have I minus going to I2. Obviously this guy's got Mn, this one's got Mn. So we would take our MnO4 minus to our MnO2. So these would be our two half reactions. Again, usually a good idea to sort of get an idea as to what's being oxidized, what's being reduced. Oxidation number for the iodine on the left there is -1. Oxygen here is -2, that's -8. And a -1 overall means that that's a +7 for the Mn. I2 is a 0 oxidation state. Oxygen over here is -2. There's two of them, is -4. It is a +4 situation happening for the Mn. So again, in terms of oxidation and reduction happening, the I is going from -1, which is here, to 0. So it is going through oxidation. And just to verify, our Mn is starting at +7, which would be over here, heading to +4, which would be reduction. So this is really our oxidation half reaction, and that is our reduction, meaning that the I- is our reducing agent, and the MnO4 would be our oxidizing agent. Any questions on that there? All right, so we're going to roll through our steps here, just like we did on the previous.
Sorry, I do have one question. How did you get +7 for manganese?
For over here, this.
Yes.
Yeah. So let me just get a fresh arsenal marker right here, so I don't mess up too much on that page. So MnO4 minus, right? So again, this entire thing has a -1 charge. Okay. So the oxygen again is going to have that oxidation state of -2. And since there's 4 of them, that's going to give you a -8 for like the oxygen side. So basically what we have is -8 for the oxygen side. The overall thing does need to equal -1. So to really get us to -1, the Mn in this case does need to be +7. 8 negatives and 7 positives leaves us a -1 that's left over.
Thank you. That was sticking me in the side the entire time. Thank you.
No worries. Other questions? Okay, so now that we, again, it's a good idea to really sort of understand, what's being oxidized and what's being reduced. So as you go through the process here, you can really kind of catch yourself, hopefully, if you make a mistake in terms of really when you start to add the electrons at that step. So the first thing we really want to do after we kind of split it off is to balance every element other than oxygen or hydrogen. In the case of the iodine, we do need to put a 2 in front of it. That gives us 2 iodides on both sides. In the case of the Mn, we do have 1 on each side, so we're good on that. We now can proceed to balance the oxygen. So remember, in this weird, funky approach here, we're going to use water to balance the oxygen. So whatever side of the half reaction needs more oxygen, that is where we're going to add the water. In the top half reaction, there's absolutely no oxygen at all, which means we don't have to worry about it. In the bottom half reaction here, we have 4 oxygens on the left and 2 on the right. So what that means is we need 2 waters on the right-hand side. And the purpose of adding those 2 waters to the right-hand side is to give us the correct amount of oxygen now on the right-hand side. And if we just look at the oxygen, there's 2 oxygens in the MnO2, and there's now 2 oxygens in the water. That's a grand total of 4 oxygens on the right to match the 4 oxygens that are on the left-hand side here. Because we added the water, as we talked about, so we are not messed up in terms of the hydrogen, we do have to add 2 H pluses for every water that we added. So in this case, we added 2 waters, which means to the left-hand side here, to make sure that we didn't mess up the hydrogen aspect of it, we need to add the 4 H pluses. And now we are balanced in terms of the hydrogen also on both sides. Any questions up to that point? Okay. So at this point, we've balanced all of our sort of elements. The next thing that we want to do is we want to add electrons, as we talked about. So again, we're going to add electrons to this guy. I'm just going to rewrite it to give me just a little bit more room here. You obviously don't need to rewrite it in your paper if you don't want to, but we're just going to go kind of move it to the center so I don't get so squished. Do that. We'll do this. All right, so remember, and it also gives me something to scribble on up here. The easiest way to balance it is, again, we're going to have these negatively charged electrons. We already know from figuring out that it's oxidation that electrons should end up on that side. And for this guy, electrons really should end up on that side because we already determined that. So let's figure out how much we need. Left-hand side up on top is a -2 overall charge from the 2 times -1. Overall charge over here is 0 since iodine has no oxidation state is 0. That means, as we predicted, we need to add the 2 negative charge to the right-hand side because it is oxidation. That now gives the right-hand side overall charge of -2 to match the -2 that's over there on the left-hand side. So I'll add it to my bottom equation as well. Any questions on that one there? Now, looking at the second equation, the reduction equation, that is going to give me a +4 for the hydrogens. Again, because this overall thing has a charge already, it's taking care of all the individual sort of math that you would have to do. And we know this overall thing is -1 here. So if we add up on the left-hand side what we got going, that's +4 and -1 is +3 on the left-hand side. On the right-hand side of the bottom equation, this is 0 since it has no charge, and this is 0 since it has no charge. So we really want to get the left-hand side to 0 in this case. And to do that, we would need to add 3 electrons to the left-hand side. Also makes sense based on what we previously predicted that that's where we should add them. Any questions on adding the electrons here? Now that we've added the electrons, we're almost to the part where we're going to add these guys back together. Before we could add them back together, though, one crucial thing is we need the same number of electrons in each half reaction. So the same number of electrons is needed. So like we did before in this case, and again, I'm going to rewrite it here, just give me a little bit more room. We're going to need to multiply actually both half reactions by a number. I have 2 electrons in the first one, 3 in the second. Common number there is 6. So to get my first half reaction to 6, I need to multiply everybody by 3. To get my second half reaction to 6 electrons, I need to multiply everybody there by 2. So doing that and just copying it down, 6 iodides, distributing that 3 to the other side, 3i2 plus 6 electrons. Distributing the 2 all the way across here gives me 6 electrons plus 8 H pluses plus 2 MnO4 minus, taking that 2 all the way to the other side as well, 2 MnO2 plus my 4 waters at this point. Any questions up to that step? Good news is now that we are the same electrons and opposite sides of the arrow, we know as they should completely cancel out. And this should now leave us technically the equation that would be balanced for acidic conditions. And we're just going to keep everything on the left-hand side of the arrow on the left-hand side of the arrow. So 8 H pluses plus 2 MnO4 minuses plus 6 iodides. Everything on the right-hand side of the arrow, 3i2 plus 2 MnO2 plus 4 waters. And I'll box it, even though I didn't ask for it in acidic, but it's a good idea just to give you an idea. This again would be us balanced in acidic conditions. Again, we do know it's acidic conditions because we see in the overall reaction at the end, H plus. So again, we know that's acidic. We can take a second here just to make sure everything is balanced. If we look on the left-hand side, we have 8 hydrogens on the right-hand side, 2 MNs on the left, 2 on the right. Oxygens, 2 times 4 is 8 on the left. We have 4 oxygens in the MnO2 and 4 in the water, which is 8. 6 iodides on both sides. Overall charge on the left-hand side, we got plus 8 here. I'm too close to the bottom there. I'll go over here. Plus 8 from the hydrogen. We also have -2 for the 2 MnO4s, and we have -6 for the 6 iodides. And that gives us a grand total of, looks like 0. Right-hand side, I2 has no oxidation state. MnO2 is neutral. Water is neutral, which means we have 0 in terms of charge. So if you were doing this problem and they wanted you to balance it to acidic conditions, you would put a box over it like I just did there, and we would be balanced at acidic conditions. Any questions up to that point? Now, obviously, we're looking for basic conditions, so we're going to continue on here, and we're going to continue on, and I'm going to try to recopy this here. So what do I got there? 8 and 2 and 6. So I have 8 H pluses plus 2 MnO4 minus plus 6 I minus, right? And on the other side, 3, 2, and 4, huh? So 3, 2, and 4. I hope I got that right there. Looks like it. 4, 2, 3, 8, 2, and 6. All right. So remember at this point, we really were asked to do it in basic conditions. And the easiest way is to do the acidic like we just did. And now we want to add OH minus to both sides. And again, remember, it's going to be equal to the H pluses that we have. So when we look at our equation here from acidic, we have 8 H pluses, and that is exactly how much OH minus, again, we're going to add to not just one side, but both sides. Remember, the side where the OH and the H pluses will combine to make water. So that's going to give us 8 waters plus 2 MnO4 minuses plus 6 I minuses goes to 3I2 plus 2 MnO2 plus 4H2O and 8 OH minuses. Just like normal, usually we got a water situation that will reduce. That is going to leave us 4 waters on the left-hand side. Again, it's essentially like subtracting 4 waters to each side, right? Those guys cancel, and that leaves us with the 4. Plus 2 of this, plus 6 of that, and 3 of those guys, a couple of those guys, and 8 of those guys. That's a really bad looking 3. There we go. And again, if we did not mess anything up, this should be our balanced equation in basic conditions. So again, if we count up everything, I got 8 hydrogens on the left. I got 8 hydrogens on the right. I have 4 oxygens there, plus 8 more is 12 oxygens on the left. I got 4 oxygens there, plus 8 more is 12 on the left. 2 MNs on the left and 2 MNs on the right. There we go. I got my left and right correct. And 6 iodides on the left and 6 on the right. And overall charge, left-hand side, 0 for the water, -2 there, -6 there. That's a -8. Overall charge on the right-hand side, 0 for the I2, 0 for the MnO2, and 8 times -1 is -8. That is a double check. We're good both ways. This would be our balanced equation in basic conditions. Again, it's basic because of the hydroxide that is present at this point. Question on any of those steps or how to balance these redox reactions. It seems really crazy, but it is definitely doable. The key is to just make sure you take your time and stuff and copy things correctly. That's sometimes, you know, where people make some errors. Any questions on any of that there? Okay, so the purpose of us going over this is obviously this is stuff that you do need to know how to do. It is also pretty much what study assignment F is all about, balancing these type of reactions. If you need more room for study assignment F, you obviously could do it on a different piece of paper, a separate piece of paper, but it is pretty much what is all involved there in study assignment F. Before we wrap it up here for tonight and the torture of listening to all this, I did want to go over study assignment F here and a couple of things that confuses people sometimes when they read the problems. So I just want to make sure everybody's on the same page and understand sort of how to approach the problems. We won't do one or anything like that, but I just want to kind of point that out to you. So first off, the first one that sometimes confuses people is actually question number 1 on study assignment F. First off, when you go to question number 1, there's a lot of stuff that it's asking you to do. It's asking you to give the oxidation number. So oftentimes people forget that. So underneath each element, you've got to give the oxidation number. You also need to identify each one as either a oxidation, half reaction, or a reduction half reaction. So sometimes people forget to do that. And then you need to write the balanced half reaction on the line in acidic conditions. So basically question number 1 is just like half the reaction basically. So it's just one half reaction. You don't have the other half reaction. Those reactions that you see may be a oxidation half reaction, maybe a reduction half reaction, but they're basically just one of them. So for example, if you look at the very first one, Cl minus and ClO3 minus, let's first figure out, is it oxidation or reduction? So if we look at oxidation number, that's -1. Oxygen is -2. That's -6. That is a chlorine with a +5 happening in that situation. And what that means is obviously, right, if we follow our number line here, it is going from -1 to +5. That means that this is a oxidation half reaction, right? By the way, those are all things that you need to do. Give the oxidation numbers, identify it as a oxidation half reaction. Then what you need to do is balance it. So how do we balance it? I kind of lied. We'll go through it real quick just to make sure. We're basically just going to pick it up what we were just doing. So the first thing we would want to do is balance any element other than oxygen, which is not the case here. We then would want to balance the oxygen by adding water. So we would add, in this case, 3 waters to the left-hand side for the 3 oxygens. That would also mean that we need to add 6 H pluses to the right-hand side. And now we need to add our electrons. So overall charge on the left-hand side is -1. Overall charge on the right-hand side is +5. That means that we actually need to add 6 electrons. +5 and -6 gives us a -1 to match the -1. This is the balanced half reaction that you would put on the line that's in there. You're basically doing just, half of the whole thing basically, right? So we're taking each of these half reactions in question number 1 all the way through the adding electron part. Any questions on what to do in number 1 there? Okay. Now let's talk about numbers 2 and it's just 2. I think it's just 2 with a bunch of them, right? I think, well, obviously, yeah. So number 2, and a couple of things that you will see that you may not understand as to, what you need to do. So let's take a look first off at number 2A. And the equation that's given to you is this equation right here, which is MnO4 minus plus SO3, this is 2A, 2 minus plus H plus and some water and SO4 2 minus plus Mn2 plus. All right. Now, I don't want to say it shouldn't be there, but it shouldn't be there. There are a couple of things that's in this equation. So it's there for a reason. but it messes people up. And it's this part and this part. All right, so what do these two things basically mean in this case? Well, I see H plus. So what does that mean when we see H plus? It means you really should balance this in acidic conditions. So in a number of these on question number 2, you'll see an H plus in the original equation and maybe a water on one side. By the way, H plus could be on the right, water could be on the left, whatever it may be. But when you see the H plus in the equation, it's basically just telling you that you should balance this in acidic conditions. So really what you should do is rewrite that equation and take that out and just start with this equation. So take it out to begin with, start with this equation, and then proceed through all the steps that we just did, okay, until you get it balanced in acidic conditions. So you would split it off into its half reactions, right? You'll add your water, you'll add your H pluses, you'll add your electrons, you'll add them back together, and boom, when it's all said and done, you'll have your balanced equation that you'll hopefully put a box around. Any questions on that? Now, because he put this into the original equation, you could kind of check yourself when you're done balancing this correctly. Your H plus in your final equation should be on the left-hand side, and your water should be on the right-hand side. So you could kind of check yourself at the end if you want, but oftentimes confuses people. So just take that part out, start with what's left in terms of the equation, and then proceed through and balance it like we talked about. Question on that. Now, the other thing that you might see is one that represents a basic condition. So if you look at 2E, for example, you have this equation, Bi plus water plus MnO4 minus Bi3 plus MnO, no, too many O's, MnO, that's it, plus hydroxide. So same idea here, except that what we see is hydroxide and we see water. What this is telling you is you should balance this guy under basic conditions. So again, to start this problem, take them out and start with just this guy. And again, go through all the process that we just talked about and get yourself the balanced equation in basic conditions. So just like the previous one, you would split it off into its half reactions. Add your waters, add your electrons, add them together, add your hydroxides. And when you're all said and done, you'll have your balanced equation that hopefully you box. And again, you could use this to check yourself when you're all said and done. Your hydroxide should end up on this side, and your water should end up on this side in your balanced equation. Question on that? If there's no H plus or OH minus in an equation, you could probably assume that it is neutral, and you could just separate it out, add them back together, and that things will balance out correctly. You won't necessarily have to add waters or anything like that. It'll just kind of balance. It'll be more of a basic redox reaction. You don't have to add the waters or anything like that. Any questions on sort of what you need to do in the study assignment?